Hello, surveying students. This is John Hannon. This is just kind of an intro video to Chapter 7, which is titled Horizontal Control Surveys. And I thought I would just briefly go through a few things. Please do all the reading. Right now I'm going to concentrate, and you should concentrate your reading on Section 7.1, which is just the basics of traverses, and 7.2, traverse closures. Okay. If we have to take more time for this chapter, that's fine. Right now I would like for you to concentrate on these sections, and if you've already done the reading, practice some of the problems. You can see how the previous chapters brought us to this point. They were cumulative in nature in what we were doing. Probably not going to spend a lot of effort on section 7.3 or side shots. Not sure at this point about triangulation and trilateration, even though I want you to know what they are. It's very, very important. And we may defer GPS, GNSS. That could be its own chapter, actually. So we'll definitely cover GPS later, but again, the whole point, 7.1, 7.2. So please, when you go through here, do your reading. If I can get this thing off there, thank you. And what we're talking about is control points, a control survey. Okay? That is different than what you would encounter on a job site, most likely. You're going to be coming off the control that a surveyor possibly does in a traverse. Okay? So the project job site, you can't just go out there and start surveying. You have to have a point of reference that's true, that links your measurements into the whole scheme of things. And that's what we call control. You have to come off of control, right? Sounds crazy, but again, that's the name of the chapter, control surveys, right? And it talks about one of the best ways to one of the few ways to establish control is from benchmarks or control monuments that are placed throughout the country. There are control monuments on the Southern Miss campus here, and when we have people out with instruments, we use that control to do our traverses. Then we know that we're tied into something real. Okay, so a lot of times you can use GPS when you come off of control, or you calibrate your GPS equipment from control. You have to check it on something that's true, something that's just not arbitrary. Okay. And so a traverse, it tells you here, a traverse survey involves a connected sequence of lines whose lengths and directions. So we're dealing with both of those, right? So the legs have to be measured in length. We can give them bearings if we measure the angles and know what quadrants they're in and so forth. All right. And I'll draw one here in Civil 3D. It might help solidify in your mind how this works. Okay. An interconnected series of lines called courses. So these words are important. Running between a series of points called stations. Right. So the language is important. And it talks about different types of traverses, open or closed. And then there are two types of closed traverses, loop and connecting. And we're going to concentrate, for now anyway, on loop traverses. Okay. Understand what witnessing a point means. Okay. So sometimes it's necessary to put the control point in perspective so future surveyors, future people doing layout can find it to establish their control. And there's some diagrams here. Please look at those and understand what they're trying to emphasize with those diagrams. And so there's a couple of pages there. And then we get to figure 7.3, and this is a very simple diagram of a loop traverse. So it's kind of a polygon once it's closed, like this. And it may start at A, it may start somewhere else, but typically the direction of the survey itself is counterclockwise. So typically it would go in this alphabetical order this way. So you would set up a point here, set your instrument up at A, for instance, okay, and you would establish E with a back sight, and then you would turn this angle at A, angle EAB, you would turn this angle and establish this point, all right, starting your counterclockwise direction. And you would backsight to A, get your transit vernier set up to turn this angle at B or ABC so that you can get the line of sight to this distance at C, and so forth and so on around the loop. Okay, and that's a traverse. And the rest of the chapter that I want you to concentrate on now is making sure that this thing closes correctly. So if you started at A, for instance, started turning these angles, measuring these distances, and come back up here, and you need to turn this angle and get back to A, do you come back to the same spot? If you have a defined length and a defined angle, sometimes it doesn't end up perfect, and you have a gap between where you start and where you close. And so it starts talking about how you calculate that error and what you do to adjust the traverse so that the control is closer to perfect based upon the error that you've measured. And then basically I want you to know these 6 steps. I'll probably show this in a different video, but this is the meat and potatoes of what I want you to get out of section 7.2, which really that's all it is. It's computing the angular error and adjusting the angles, then computing new bearings or azimuths, then this is new to us, latitudes and departures, determine the error of closure and the accuracy, and then adjust those latitudes and departures, and then computing station coordinates. So maybe for some of you this will tie some things together. You know, I know it does for me, actually. So please please read 7.1 and 7.2 in its entirety, and take a look at this, for instance. This is figure 7.6, an example of a loop traverse showing the original unadjusted field data. Excuse me. So what I might do is I might draw this in Civil 3D just so you can get an idea of how, let's say you've got one instrument a prism or a rod person. You've got two people in the field that are going to do, they're going to create this horizontal control or this loop traverse. So let me take that. You might, if you have your book with you, or you can look at figure 7.6. The way I'm going to do it is I've actually got control already on the diagram. And what is my control? Because I want to set points, I want to set all these points and turn these angles. My control, it says here assumed, all right, but maybe it's maybe these are monuments. But even if it's assumed, this is my control. My starting place is this bearing right here. You can grab Civil 3D and try to do this without having a bearing, and you'll start to get the idea of what it would be like in the field. So I'm going to come up here, change my background to white. It still doesn't give the color contrast that I like. I haven't figured out how to change one of the little cursor colors, but I'm going to come in and I'm going to create a line by bearing. Okay, and Civil 3D shows you when you make these choices, it shows you the steps that you're going to take. The first one is you have to specify the quadrant, right? Northeast, southeast, and so forth. And then you give it the bearing and a distance, and it'll set it in the drawing for you. And then once I do that, then I'm going to pull the traverse. You know, the part that doesn't show up very good won't let me take my cursor there, but when this little picture pops up, you can see the instrument here. It's in blue. On my screen it's yellow, and it's hard to see, but you can see the little blue instrument. It's like on a tripod, and the thing in pink is the prism or the rod, and then the distance that the instrument's measuring between them, or the angle that it's measuring between them, and so forth. So I chose I think I chose the right one. It wants to know the quadrant. All right, so it's the bearing is southeast, so that's in quadrant 2. So it knows it's in that quadrant. Now it wants to know what the bearing angle is. So I'm going to say 81.4215 for 42 minutes 15 seconds. And I hit enter. And you can see it's snapped to that angle. Now it wants to know a distance, so I'm going to say 971.26 feet, I assume. And now I've got that bearing set. Okay, I might move it down a little bit instead of panning the screen. And I could keep doing bearings, but the drawing, figure 7.6, just shows distances and angles. So I'm going to come up here, and this is kind of the way they do it in the field. I'm going to create my line by angle and length. And so if I hit this point, and I hit this point, now I can start turning this angle at E. It wants to know the angle. So I just look on the diagram, that's 96.3845, and it wants to know a distance, and distance EA, which I'm drawing, is 783.32, and there I go. Now I can turn my next angle, which is angle EAB. I'll just type it in. I could do it with the cursor, but I'll just type it in to be more precise. 64.5330. And now it wants to know a distance, which on the diagram is 690 feet and 88 of a foot. And now it wants to know this interior angle. So you can see typically the traverses, this is important, are interior angles. You could do them with exterior angles, but that's really not the practice at all. And they're turned to the right. That's important. So the direction of the traverse is counterclockwise, turning angles to the right, just like it's showing on here. So I need to put in this big angle at B in figure 6, 206.3515, and then I'll give it the distance of BC, which is 616.05, and I'm getting real close. Now I got to turn this angle at C, which is 64.2115, and it wants to know the distance now, so I can close back at D, and that is 677.97, and there's my loop traverse. Now what's interesting is if you look here, get this guy out of the way. If you look right here, looks like I've got some closure error right here. And talk about that in a future video. In fact, this program can actually help us. We're going to learn how to do it the hard way, by hand, and then we'll let the computer do this for us in lab. So let me see. The rest of the chapter is going through those 7 steps. When I did them, computing the bearings and the azimuths, this part here, I would follow the example. This was probably the most challenging part for me till I figured it out, and it's just, it's so simple. But it's hard to do it for the first time. Don't let all these strange formulas intimidate you, because it's really simple stuff. It's just coordinate math, and it ends up giving us coordinates like these, northerlies and easterlies. These are just coordinates on an XY grid with angles. So don't let that stuff intimidate you. Once you do it, practice it a couple of times. It's not bad. One of the exercises, either in the theory or the lab, we'll be setting up a table to accomplish these 7 steps. Let me go back up. Excuse me, 6 steps. Debatable, might be 7. But this stuff right here you can do in one table. And of course, I'm going to jump into a spreadsheet. Anyway, just a little introduction, and just emphasize for now on section 7.1 and 7.2. As far as practicing goes, please read all of the chapter, to concentrate on 7.1 and 7.2 for now. All right, I hope this was helpful. Thank you very much.